on section 2.6 here, a related rates problem, and we're doing example 5 in your notes. And this one has a winch that is reeling in rope. The winch is positioned 20 feet above the water, and it reels in a rope that's attached to the boat. The rate at which it reels it in is 2 feet per second. How fast is the boat moving when the rope is 45 feet long, and then at the precise point when we're at 22 feet of rope? Okay, so I want you to see an animation of this so you can get a picture of what's going on. Let's hide that dx dy right now. I'm going to reel in the boat. Just watch it. Does the boat constantly move at the same speed as it's being reeled in? Well, no, you can definitely tell as it gets close in this region, all of a sudden it just moves very, very quickly, almost faster than what your eye can follow it. Zoom. Okay, let's lock that on. I want to show you the dx dt. Okay, so if I show you dx dt, that is the rate at which the boat is moving. Here would be dx dt, or another way to think about it is the change of x over the change of time. It's a rate, isn't it? Feet per second in this case. So what I notice is the rate stays fairly steady as we move out in time. This is a fairly steady rate that the boat is moving. Then all of a sudden that rate just changes dramatically. It is negative because it's closing in. X is getting less and less. So that would be the reason for the negative dx dt. It's moving in a left-hand motion and closing in the gap of x. So that's the purpose of the negative. The largeness of the negative as we reach down in here resembles that fact that as this boat's reeling in, all of a sudden, happens really quick. So watch this time piece as this is traveling over. All of a sudden, we reach a time point where it just, changes dramatically. So we kind of got an idea of what's going on. Let's try and go draw a picture for ourselves on our paper here. We have a right triangle that I'm going to position as such. The rope would be right here as it reels in. So I'm going to call this amount R, this amount X, the horizontal distance, and then we've got the reel that's reeling in the rope. So here's our winch that's reeling in the rope, and we're 20 feet above the water. This is a fixed amount. That is never going to change. It's not varying, so that can stay at 20. We have the boat out here, and it's reeling in. So there's kind of the scenario. Now, it says that the rope is attached to the boat, and it's coming in at 2 feet per second. So dr dt is a known quantity. It is 2 feet per second. And since it's reeling it in, it's getting less and less. I'm going to call that a negative 2 feet per second. Let's see. What else do we need? I guess we want to know when the rope is, how fast is the boat moving? Well, this would be the boat speed here, wouldn't it? This horizontal component. So dx dt is going to tell me the boat speed, and then I want to capture it when we are at a rope of 45 feet long, and then also a rope of 22. I have a Pythagorean theorem, so I can relate these quantities by using the Pythagorean theorem. And that would be a squared plus b squared equals c squared. See if you can write the equation down for your triangle. Pause this for a moment and then come back and look at mine compared to yours. Okay, that is what I came up with. 20 squared plus x squared equals r squared. If I take the derivative to get into my rates, I would have to do implicit differentiation. Derivative of 20 squared would be 0, because that's a constant being the derivative of a constant. Next, I'd have 2x dx dt equals 2r dr dt. We want to know what dx dt is. So I could solve for dx dt, couldn't I? And I'd have 2r divided by 2x, moving that 2x over, dr dt. Well, the 2's will cancel, and we're going to be left with r over x. So dx dt is going to be a relationship between the rope length and x, the distance it is from the dock or the winch itself, and then dr dt. I know dr dt, it is -2 feet per second. I know the rope length was 45 when I was interested. Now, how do I get r? I'm sorry, how do I get x? Well, that we can do at this moment. Now we want to let r be 45. So I can find x at a precise point. Find x when r was 45 feet. Pythagorean theorem again. 20 squared plus x squared equals 45 squared. Solve for x squared. 45 squared minus 20 squared. X will be the square root of all of that. So grab your calculator and, okay, I just put mine in the calculator and I'm coming up with the square root of 1625 is what I'm seeing. So square root of 1625. That we can place into our derivative equation over here. So dx dt is equal to 45, the rope length, divided by x, and x is the square root of 1625, multiplied by -2, and that would be feet per second. And that should get you an answer. My answer came out around 2.233, and it is negative, of course. Very good.